Okay, it's just about 9 o'clock, or actually 7 o'clock in Arizona time. And welcome to week 13. Can you believe we're here? CYBV 473, Violent Python. And we're going to go ahead and get started. And I'm going to do two things tonight. One is we're going to continue this whole theme of steganography that we kind of skipped a week over in doing the NLTK stuff. So we're going to go back and do some other steganography stuff this week. Just certainly part of Violent Python. And we're going to do this week, we're going to actually explore that using MP3 files, kind of introduce MP3 files to you in a way maybe that you haven't seen before. And we all obviously play them in our car, on our iPods, on every device that we carry around with us. But there's some aspects of that that you might not know about. So I'll kind of go over some of those with you. In addition, I'm going to just do a quick overview of the solution. Obviously, your assignment is not due until tomorrow because I gave you that extra day because of Veterans Day. But I will go over the solution. So if you want to cheat, you can. I'm not going to post the solution until tomorrow night, but I will kind of go over that with you. So again, let me actually just demonstrate it for you first, which I think I've already done. So I'll just kind of go over a couple of the functions that you haven't seen and where most of the questions that I've been seeing. So I'm going to say /corpus, which, as you all know by now, basically goes out to that directory and collects those files and actually produces a corpus. Corpuses are important because that's kind of the data that we have. Some corpuses can be extraordinarily large based on the files and information that we bring into those. It can be entire books or whole sections of libraries, etc. But in this case, it's just basically 4 transcripts from the O.J. Simpson trial. So what we've done before is we've kind of looked at what the size of the corpus length is. That's the number of bytes that are in the corpus itself. In other words, the number of characters that were there, the number of tokens, basically the number of individual words or phrases. Some of you have seen just maybe punctuation, that kind of thing. Then the vocabulary size, which is basically the unique items that were in that corpus. A couple of the ones that I haven't gone over is let's go with word occurrence. If I wanted to know how many times the word glove appears, it comes back to 0 times. And the reason it did, because as I mentioned before, the search functions are case sensitive because in trial transcripts, most of the time, those trial transcripts are all caps. I don't know why they do that or where that came from, but they do. I'll go through, show you how to do each one of these. So then that was word occurrence. Let's go with concordance, right? So in this case, if I wanted to use glove again, we'll go take a look at the code for this. It's going to basically, as I showed the other day during the session, it's going to show you all the places where glove appeared, and it's going to have so many words before the word glove, how it appeared, and after. If I go look at that code that actually did that, this was the concordance. And again, it's only a couple of lines of code here. And so we're using the self text corpus, and we're using the function concordance. We're passing in the word that we want to concord and how long each line will be. In other words, in this case, there'll be 100 words before, 100 words after the word that was found, and then a maximum number of 100 occurrences. You can set those to whatever you want. So that's how you actually perform concordance. I come back to the code here. We'll go to the next one, which is, I believe, similarities, right? So we'll do similarities next. Again, it's asking for a word, and this time we'll use gun, and it's going to basically compile the first 200 similarities. So in this case, when we're doing similarities, think about it as thesaurus, right? Think about it as kind of like thesaurus, words that are related to the words that I'm looking for and what their context was. And again, the way we do that with NLTK, the National Language Toolkit, we use the function similar. Again, from the text corpus, my word, and give me the first 200 similar sentences that contain information that surrounds that word. The last one was that we were going to do was the vocabulary. And let me actually set a breakpoint in the vocab one, because this one a lot of people had questions about. We'll do 7 and it'll generate vocabulary. So when I step through this, I'm just going to create a pretty table that is vocabulary and the number of times it occurs. I'm going to use the vocab function from the text corpus, and it's going to give me a dictionary with the vocab frequency. And so because it's a dictionary, I can iterate through the dictionary, and I'm going to get word and frequency, key, value, right, in this particular case. If I look at the first one, the word that it found was asterisk, okay, and the frequency was 2,912 times it found what it thought to be a word called named asterisk. See if there's anything interesting here. So this would be lost, like in Los Angeles. How many times did that occur? 41 times. So I'm adding those rows as we go to the pretty table. And so if I then eliminate the breakpoint there and just say go, I can print out the table. And because, oops, hang on. Because I printed out the table sorted by occurs, right, which was the first field, which is the second field within my table, which was the value, and I do a reverse sort, the ones that occur most often will come to the top of the table because I'm basically sorting based on the occurrence. So I don't go too far here. So these are the words that occurred most often within their evidence. Occurred 521 times, defended 452 times, statement, defense, some special characters, which you could have filtered out if you wanted to. In other words, when you got to this point in your code where you're adding the word and frequency to your table, you could say, hey, if it's, you know, less, if it's not characters or it's less than a certain size, then you could have filtered them out if you wanted to, but it wasn't necessary. I didn't. I wanted to know what all of them were there. So, you know, there's crime, it occurred 90 times. Now remember, this wasn't the entire corpus. This wasn't the entire trial transcript. I selected 4 days of the trial because it was, you know, 30-day trial or something. So it's only a few days. You know, murder occurred 68 times, credibility 66 times. So you kind of get the idea. So that was the assignment. It was basically just kind of to get you to dabble a little bit into NLTK, just to kind of brush the surface of the capabilities that are here. As I mentioned a couple of times already, we use this extensively and all kinds of capabilities within it, within the machine learning class, which is CYBV 474, in order to be able to analyze text and extract meaning and that kind of thing from text. So any questions about the assignment that you're currently working on before I jump into this week's presentation? Elizabeth, I know that you're there, and I noticed that you basically responded to a couple of the questions as well. Those were right on the mark as usual. Thank you for doing that. And I know there are several questions about some specifics about format of the output and whether you should include those words like 1994 and that kind of stuff in the result. And that was great. Thank you. Any other questions? Great. Let me bring up this week's briefing and we'll get into MP3 files. So MP3 files, you know, we tend to think about them as music. We tend to think about them as speech or podcasts or whatever that are MP3 files, but they're much more than that. So just kind of giving you some of the basic definitions. MP3 is an audio encoding format that employs lossy compression to reduce the size of the audio, and the resulting MP3 content can be used to store files or stream content over the internet. More formally, MP3 is referred to as MPEG-1 and MPEG-2's audio 3 layer. So it's really part of the MPEG standard that is out there, and that's where it actually, all of the details regarding MP3 are defined as part of MPEG. Just if you're kind of an audio buff and wanted to know a little bit about that. So when we look at this, MPEG is the Motion Picture Expert Group that created this standard that defines standard for both video and audio, especially as it relates to compression. And these standards are most utilized forms of video storage and transmission today. If you look at MPEG and MP4, it is certainly one of the most popular. Certainly Apple has AVI and a couple others that are out there that are also useful, and they follow similar models. They're just different standards, but this one is defined by the Motion Picture Expert Group. So what we're really interested in is the internal structure. Nobody's saying anything, so I want to make sure you guys can hear me right and see my screen. I haven't.
Yes.
Okay, great. I forgot to do that sound check at the beginning, so I could have been the last 10 minutes talking to myself, but thank you for letting me know. Really important when we look at MP3 is the internal structure. And we're really going to focus on the ID3 header of MP3 for storing hidden content here or doing steganography. So the internal structure consists of information associated with the audio file. And again, we're going to be focusing on the ID3 header and the ID3 frames, where the MP3 header and the MP3 data is basically the compressed audio information that is part of each frame. Okay, so we're not going to talk about that because it's really, really difficult to hide information in that because each frame is really small and they use different codecs and compression mechanisms. So people have found that it's very difficult to hide information in the MP3 data. There's multiple different versions of MP3 ID3. There's several popular versions of what that ID3 header format is and the associated tags. So what you might be surprised with is the flexibility and the plethora of information that we can store in the ID3 frames. Probably some of you might have cars that have MP3 players, and when you play the car and it has a video screen, it'll actually show you pictures of the artist or the group and that kind of stuff. There's lots of information here. Obviously, there's lyrics. You know, if you're using certain players, basically in the lyrics were included in the ID3 header, it'll actually play and synchronize those lyrics with the actual song. So things like, just to give you a summary of this kind of stuff, we can have the album, the artist, the genre, the tag version, the title, the year. All of this information can be embedded in the ID3 frames, and it's up to the artist and the producer to determine what of this information is going to be included. So it's a very flexible format. You can have many different fields here. You can have many different tag types. For example, one of the things we're going to be looking at here is the actual tags that are associated with the image content, right? So that, you know, we can actually see images and we can embed multiple images within a particular MP3 file. So this just kind of gives you a quick little summary of some of the tags, not all of them, that are available that we can encode information in and we can use them for good or evil. We can hide information in them, or we can use them as they were defined to do. So like many data structures, whatever it happens to be, MP3 files have really very little, if any, security built into them. If the stuff that is invented is related to digital rights management, and it's basically a joke. It's certainly not like the Apple format that basically is tied to hardware. So even with DRM, most devices except Apple do not enforce the rights. So you can take an MP3 file, you can copy it, move it everywhere we want to, and nobody ever says anything, right? You can even modify it and alter it and do a bunch of things to it, right? And be able to play it on multiple different devices and platforms, pretty much the wild, wild west. So let's talk a little bit about the vulnerabilities that exist in MP3 files. If I want to embed hidden text content in any one of those hundreds of fields that are out there, it's pretty easy to do, but also fairly easy to detect if you're looking, right? If you're actually examining the ID3 headers for information that could be encoded. I could encrypt text or put that in binary content. Pretty easy to do, a little bit more difficult to detect, right? Because now I've got to detect that, hey, that was encrypted text and not just, straight ASCII, but maybe it was, encoded like ASCII. So I'm not sure if it was really something that was encrypted or not. So it could be more complex to detect. I could embed URLs to share, let's say, command and control information, because several of the fields that are within MP3 ID3 headers are designed to hold URLs. In other words, websites. So I could use that to basically hide information in there, basically a seemingly benign URL that could actually be a command and control site and being able to communicate information there. Now, the big thing is I could also embed data in the existing images that are in the particular ID3 header, or I can even add images to those MP3 files. So the complexity is moderate, and detection in this case would be hard because you would have to actually detect, and that's what you're going to be doing this week, which images within the images that are contained within that ID3 header actually contain hidden content. That's going to be actually your assignment this week, and I'm going to give you some tools to be able to do that. So you're not going to have to be on your own. So most of what you're going to be doing this week is running a script that I've already provided you, and then actually using some steganography tools in order to investigate which images contain information hidden in them, and then also extract the content of that data. So again, exploiting these tags, we can view them in a hex editor or raw. We can edit fields. For example, one of the fields that we're going to focus on is APIC, which is a field that you can identify one or more images that you want to basically place, within the file. You can hide content in the image, then splice in modified images back into the MP3. In other words, I can add new images. You can save and play those. You can upload it to a cloud player, share with others by posting it in distribution. We did this, Mike Rago and I actually gave a presentation a couple of years at DEF CON, a couple of years ago at DEF CON, demonstrating that we could hide information within an image within an ID3 header and then post that new MP3 file to Pandora, and you could download it and basically retrieve the hidden content. So there's a lot here that still needs investigating. So again, modifying that album art that's there so we can modify those images that are there to carry additional information is what this is about. So I've provided you with a Python script that's going to do some of the heavy lifting for you this week. So let me actually go ahead and run that script for you so you kind of see what it actually looks like. It's a little bit different than other scripts that you had because you have to answer a question at the beginning. So in this particular script, when you run it, it is going to, oh, I was still in the other script, sorry. So it pops up this box that you've probably seen 100 times, but just kept hitting OK. This is where you're going to type in the name of the file that you want to analyze. So I'm going to basically use eo.mp3. There's two different files that I'm giving you. eo.mp3, which is the original, right? Unmodified, unchanged. And then there's es.mp3 that I'm giving you. And that one has stegoed content, in that particular MP3 file. We're going to look at the EO MP3 file first. And the script just runs and basically extracts all of the data within there. So let's start right at the top. And it pulls out all of the ID3 header information from that particular image. So in this case, it has a privacy frame. This is basically the fake DRM that Amazon puts in. And basically gives you information about the performer, the name of the song, what was it part of? It was part of this jazz piano on essentials. That was the copyright message. The track is one of 27 that were in the set. It was done in 2010. And down here, it indicates that there were 3 pictures associated with it. APIC is the attached picture frame, and there were 3 of those that were in fact detected. There's more information here regarding the information that was in the header. This happens to be, this is Amazon's privacy frame. Basically has no information in it except Amazon.com. I haven't modified this at all. This is right from them. It's this big frame that you can encode all kinds of digital rights management information, and they encoded nothing. And then there's a bunch of more details about individual frames that you can look at both the hex and the binary. So you're going to spend most of your time this week in 2 areas. One, you're going to be looking at this first page that comes up because all of the information that are going to be hints to how you're going to extract information from the images are going to be here. So I've encoded information in the es.mp3 that is going to be different than the eo.mp3. And you're going to use that information in order to be able to solve the problem. The second thing is that when I ran this particular script, if I scroll down here a ways, part of what's in this script are all the images that were basically that I've carved out of the MP3 file. So again, I've done all the heavy lifting for you. So this was one of the images that was carved out that was here. But what I've done for you, when you run the script, it actually carves those out and puts them into an images directory, and it names them eo.mp3-1, eo.mp3.2, and eo-mp3.3. So in the original MP3 file, there were 3 images that were associated with this MP3 file, and they're actually here. When you run this script against es.mp3, you're going to have another set of images, and they'll be labeled es.mp3-1, es.mp3-2, and so on. There could be more than 3, and some of these originals could be modified, or the new ones that were added could be modified. So keep that in mind when you're actually going to go through the exercise. So you're going to be analyzing these images and the images that and the hints associated with those images that are going to be displayed mainly on this first page that you're going to see on your screen. Depending on the size of your screen, it may scroll off here some of the stuff that you're going to have to look for in order to be able to extract the hidden content from the images that are there. So that's going to be your assignment this week, is to run the script against eo.mp3 and get those images, and then against es.mp3 and get those images, and then use the information that's in this header piece in order to be able to extract that. The other thing that I provided you, because I don't want you to get yourself in any trouble here, in the content of the of week 13, I've also included a zip file of JP Hide and Seek Win. That is the Stego program you are going to use in order to extract the data. Don't download it from the internet. Don't get it from somewhere else. Use the one that I've provided, because I know that one is safe. Okay, so that's another hint that I'm giving you right up front. But in order to use JP Hide and Seek, in order to be able to extract information, you're going to have to first figure out how to use JP Hide and Seek. I'm not going to tell you how to do that. You can figure that out. And then you're going to have to understand how to enter the parameters that are going to be necessary to identify and extract information that's in the hidden images. Now, note that the other thing I want to show you is that if I view this details, all of the images that are coming out of the ID3 header of both the original and the STEG ones are JPEG files. So if you look at the ones that come out with es.mp3, the ES ones, they could be different, and you could identify that difference in several ways. And if they are in fact different from the originals, they're either new or they're altered. That'll give you a hint as to which ones that you might want to investigate. So those are all the hints I'm going to give you to get you started, on this assignment. So your task is, again, to identify which images within ES.mp3 have embedded data in them, have hidden data, and you're going to extract that hidden content. That hidden content could be an image, it could be text. I'm not going to tell you what, and I'm not going to tell you how many there are as well. So it should be kind of a good hunt, and it's again kind of a follow-on to the other SEGO stuff that we did earlier in the semester. Questions before I kind of let you go tonight, because we've kind of gone through this really quick.
Yeah, I got a question, Deshaun. Are there any specific libraries for that code? I'm usually running this on my home computer to avoid CyBV, but if I have to, I'll get in there.
Yeah, you can you can bring everything to your local machine. That the Stego program that you need is Windows. That is a Windows program, so you just have to make sure that you're running that on Windows.
Okay, thank you.
Yep. Any other questions? Okay, maybe you'll have more questions by Saturday. I will be doing the Python tutoring session on Saturday. So if you have questions, you can come to there, and obviously we'll have the office hours on Monday. If you have more questions once you dig into this, remember last week's assignment is due tomorrow. So I'll post the actual solution to that after those assignments have been posted. And in this one, make sure that you go back and review the recording, because literally all of the answers to the quiz are in the briefing that I just went over, talking about MP3 files and whatever. So as long as you paid attention during the briefing or kind of go back and review it, you shouldn't have any problem with the quiz. So I kind of mentioned, don't take the quiz until you've either reviewed the presentation or participated in it. Any other final thoughts? Anything, Elizabeth, anything from you that I missed in the review of last week's, or anything here that you think would be an important hint?
I don't think so. I think you covered everything. This assignment is kind of tricky, but it's a lot of fun. So I just want to put that out there for the students that attempt it. Or I mean, everyone's going to attempt it, but I remember doing it last year or earlier this year, and I thought it was a lot of fun.
Yeah, it is a fun assignment. It's kind of like it's kind of a hunt, and you have to think. You have to really examine the difference between the original header and the that's printed out and the new one, to see those differences, and then think about how you would apply those. So it takes a little trial and error to get it right. So don't get frustrated. Just keep at it and you'll get it. And it's kind of fun when you get there. So thanks, Elizabeth, as always. All right. Well, if there's not anything else, I'm going to give you like another half an hour of your life back. So enjoy that. Have a great evening, and look forward to seeing you on Saturday and during the Monday office hours. And if you have any questions, fire them off to me or Elizabeth or both, and we'll make sure that we can help you out. Have a great
quick question.
Yeah.
If we could do so after the recording.
Yeah, sure. Let me shut the recording off then. Hang on. Okay. All right, everybody else, have a good night.